Section 7. Vestibular System. The vestibular system is used to maintain equilibrium or balance by detecting angular and linear accelerations of the head. Sensory information from the vestibular system is then used to provide a stable visual image for the retina while the head moves, and to make adjustments in posture that are needed to maintain balance. The vestibular organ is located within the temporal bone, adjacent to the auditory apparatus, the cochlea. The vestibular organ consists of a membranous labyrinth within the bony labyrinth. The membranous labyrinth consists of 3 perpendicular semicircular canals, horizontal, superior, and posterior, and 2 otolith organs, utricle and saccule. Semicircular canals and otolith organs are filled with endolymph and are surrounded by perilymph, much like the auditory organ. The semicircular canals are arranged perpendicularly to each other and are used to detect angular or rotational acceleration of the head. The perpendicular arrangement of canals ensures that they cover the 3 principal axes of head rotation. Each canal filled with endolymph contains an enlargement at one end called an ampulla. Each ampulla contains vestibular hair cells, which are covered with a gelatinous mass called a cupula. The cupula, which spans the cross-sectional area of the ampulla, has the same specific gravity as the endolymph in the canal. During angular acceleration of the head, the cupula is displaced, causing excitation or inhibition of these hair cells. The otolith organs, the utricle and saccule, are used to detect linear acceleration, such as gravitational force. Within the utricle and saccule, an otolith mass composed of mucopolysaccharides and calcium carbonate crystals overlies the vestibular hair cells, much like a pillow. When the head is tilted, gravitational forces act on the otolith mass, moving it across the vestibular hair cells. The hair cells are either activated or inhibited, alerting the person to a change in the position of the head. The function of the horizontal semicircular canals is to detect angular acceleration of the head, as illustrated in Figure 3-23. In this figure, the left and right horizontal canals are shown with their attached ampullae. The ampulla contains the vestibular hair cells, which are embedded in the gelatinous mass of the cupula. Vestibular hair cells differ from auditory hair cells in that the vestibular hair cells have a large kinocilium and a cluster of stereocilia. Afferent nerve fibers from the hair cell fibers carry vestibular information to the central nervous system. For example, when the head is rotated counterclockwise to the left, the following events occur in the horizontal semicircular canals. When the head is rotated to the left, the horizontal semicircular canals and their attached ampullae also rotate left. Initially, the cupula, anchored to the ampulla, moves before the endolymph begins to move. Thus, the cupula is displaced or dragged through the endolymph, causing bending of the cilia on the hair cells. Eventually, as rotation continues, the endolymph begins to move. If the stereocilia are bent toward the kinocilium, the hair cell depolarizes and there is an increased firing rate in the afferent vestibular nerves. If the stereocilia are bent away from the kinocilium, the hair cell depolarizes and there is a decreased firing rate in the afferent vestibular nerves. Therefore, during the leftward rotation of the head, the left horizontal canal is excited and the right horizontal canal is inhibited. While the head is still rotating to the left, the endolymph eventually catches up with the movement of the head, the ampulla, and the cupula. Now return to their original positions, and the hair cells are neither depolarized nor hyperpolarized. When the head stops rotating, the events occur in reverse. For a brief period, the endolymph continues to move, pushing the cupula and kinocilia on the hair cells in the opposite direction. Thus, if the hair cell was depolarized in the initial rotation, it now will be hyperpolarized with inhibition of afferent nerve output. If the hair cell was hyperpolarized in the initial rotation, it now will be depolarized with the excitation of afferent nerve input. Thus, when the head stops moving left, the left horizontal canal will be inhibited and the right canal will be excited. In summary, rotation of the head to the left stimulates the left semicircular canals, and rotation to the right stimulates the right semicircular canals. Let's discuss the otolith organs. The maculae are sensitive to linear acceleration. Recall that the hair cells of the maculae are embedded in the otolith mass. When the head is tilted, gravitational forces cause the otolith mass to slide across the vestibular hair cells, bending the stereocilia toward or away from the kinocilium. Movement of the stereocilia toward the kinocilium causes depolarization of the hair cell and excitation. Movement of the stereocilia away from the kinocilium causes hyperpolarization of the hair cell and inhibition. When the head is upright, the macula of the utricle is oriented horizontally and the saccule is oriented vertically. In the utricle, tilting the head forward or laterally causes excitation of the ipsilateral utricle. Tilting the head backward or medially causes inhibition of the ipsilateral utricle. The saccule responds to head movements in all directions. Hair cells of the saccule are excited with both forward and backward movements called pitch, and lateral and medial movements called roll. The saccule also responds to up and down movements of the head. Because of the bilateral arrangement of the otolith organs, every possible orientation of the head can be encoded by excitation or inhibition of the vestibular hair cells. For each position of the head, there is a unique pattern of activity from the afferent nerves innervating the otolith organs that provides detailed information to the CNS about the position of the head in space. Let's discuss vestibular pathways. Afferent nerves from the vestibular hair cells terminate in the vestibular nuclei of the medulla, the superior, medial, lateral, also called Dieter's nucleus, and inferior nuclei. Medial and superior nuclei receive their input from the semicircular canals and project to nerves innervating extraocular muscles via the medial longitudinal fasciculus, also called the MLF. Lateral vestibular nucleus receives input from the utricles and projects to spinal cord motor neurons via the lateral vestibulospinal tract. Projections of the lateral vestibular nucleus play a role in maintaining postural reflexes. The inferior vestibular nucleus receives its input from the utricles, saccules, and semicircular canals. It projects to the brainstem and the cerebellum via the medial longitudinal fasciculus. We now move on to vestibulo-ocular reflexes. Several vestibular reflexes are produced in response to movement of the head. One reflex, called nystagmus, occurs in response to angular or rotational acceleration of the head. When the head is rotated, the eyes initially move in the opposite direction of the rotation, attempting to maintain a constant direction of gaze. The initial movement is a slow component of nystagmus. Once the eyes approach the limit of the lateral movement, there is a rapid eye movement in the same direction as the head's rotation. This movement is the rapid component of nystagmus, in which the eyes jump ahead to fix on a new position in space. Nystagmus is defined by the direction of the rapid component. The nystagmus is in the direction of the head's rotation. If the rotation is stopped abruptly, the eyes will move in the direction opposite that of the original rotation. This eye movement is called post-rotatory nystagmus. During the post-rotatory period, the person tends to fall in the direction of the original rotation due to stimulation of contralateral extensor muscles, because the person thinks he or she is spinning in the opposite direction. Vestibular function can be tested using the phenomena of nystagmus and post-rotatory nystagmus. The Baronnet test involves rotating a person on a special chair for about 10 revolutions. With normal vestibular function, rotation to the right causes a right rotatory nystagmus, a left post-rotatory nystagmus, and the person falls to the right during the post-rotatory period. Likewise, rotation to the left causes a left rotatory nystagmus, a right post-rotatory nystagmus, and the person falls to the left during the post-rotatory period. We can also test with the caloric test, which involves thermal stimulation of the inner ear, in which the right and left horizontal semicircular canals can be stimulated separately. In this test, the head is tilted back 60 degrees, so the horizontal canals have a vertical orientation. Here with warm or cold water causes endolymph to flow, which deflects the cupula as if the head were rotated. A nystagmus occurs lasting approximately 2 minutes. Warm water produces a nystagmus toward the treated side, Cold water produces a nystagmus toward the untreated side. Concludes Section 7, the vestibular system.